How do you do, ladies and gentlemen, and boys and girls, and teachers and people? I'm Julius Sumner Miller, and physics is my business. This first lesson on kinds of waves and their fundamental properties. What is a wave? Best tell what a wave is by showing different kinds of waves. And this view we call in physics the operational. If I show you some different kinds of waves, you will get a feeling for what a wave is. Now, we characterize waves generally into transverse and longitudinal, also called compressional for a reason you will see. Now, let me show you a transverse wave. I'm going to give rise to a pulse in it by depressing a part of that tube. And watch. Something went down and something came back. The wave propagation delivered only energy. Nothing of this tube went anywhere except up and down, as I shall show you a little later. So the velocity of this transverse wave, where the particle disturbance is this way and the energy propagation this way, had a certain velocity. Now I'm going to increase the tension. And I'm going to create a pulse again. Watch it. Oh, much faster, much faster. Now, the next kind, longitudinal, also called compressional. Compressional. Let me show you why it is compressional. Remember, in the case of the transverse, the particle disturbance was up and down, and the energy propagation at right angles to it. Now I have a spring, often called commercially a slinking. I'm going to give rise to a pulse by squeezing some up, storing some energy, and letting it go. Watch now. A compressional pulse went down. I'll make it more deliberate. Oh, not only did a compressional pulse go down, but some was reflected. There it is. The reflection, indeed, we will liken in a short time to an echo. Now, the sound business we are to deal with are compressional or longitudinal waves. Longitudinal waves. Here I have an array of steel spheres on a track. They are highly elastic. I take one up the plane, allow it to collide with the system, and watch how quickly this one feels the impact of that one. Right away. Now we are to view that as the advance of a compressional wave, because that steel ball may be viewed as having a little spring inside which suffers some compression, and that compression runs away. So we have transverse waves where the particle disturbance is at right angles to the energy propagation, and a compressional or longitudinal wave where the particle disturbance is in the direction of the energy propagation. And we will see later that transverse waves can be polarized. Imagine that rubber tube whose end is fixed over there and I have the free end, and I do this to it. You know, a wave advances down the tube, and if I had a picket fence with a slot like this or a slit, you can see that that wave could go through there. But if I had it turned like this, it could not get through. And thus we discover that transverse waves can be polarized, but longitudinal or compressional ones cannot. So sound cannot be polarized. But sound waves suffer all the other properties of waves. They can be reflected, that's why we get an echo. They can be refracted, that's why you can hear a band around the corner of a building. They can be absorbed, sure, if there were an audience out here, the clothes and the hair and the whatnot, the seats that are all plushed and fancy, would absorb the energy. So I have made clear, I trust, the fundamental distinction between transverse waves and longitudinal waves, about which this series now is engaged.
People who study waves extensively in the various fields of physics and engineering are impressed by the similarities which exist in the behavior of waves in various mechanical, electrical, acoustical, and optical wave systems. These similarities are due, of course, to the basic fact that waves of all kinds behave fundamentally alike. First, I want to show you the two different ways in which waves may be totally reflected. If I start a wave at this end of the machine, that wave travels down to the far end, is reflected there, and returns as a reflected replica of its original self. I'll clamp this last cross arm to a heavy stand. The reflection is still total as it was before, but the wave is inverted upon reflection. This alternative reflection possibility should exist for waves of all kinds, and these other drawings here show that indeed it does. Note that in the mechanical situation, a clamp is a constraint preventing the displacement of the end of the wave medium. The electrical analog of this state of affairs is an open circuit termination on the end of a transmission line, preventing the flow of current at such a termination. And the acoustic analog is a rigid closure at the end of an acoustic tube, preventing the longitudinal vibration of the air. In all of these cases, the reflected waves come back upside down, and in all of these other cases, conversely, which are analogous to the case of the free end of a reflecting wave medium, the reflected waves come back right side up. You see, nature really is consistent. When two waves traveling in opposite directions on the same medium, as you see here in slow motion, pass through each other, the instantaneous amplitude of the resultant wave is the algebraic sum of the amplitudes of the two constituent waves. This principle of superposition is equally valid when one of the two waves is positive and the other one is negative. Observe that in this case, at the instant of exact coincidence, there is a momentary cancellation of the amplitude, and the medium appears to be undisturbed. Now let's have a look at the superposition behavior of continuous trains of periodic waves. With this small motor and crank, I can generate such a train of waves and reflect them back upon themselves at this end. All right, in slow motion now, here come the waves. After reflection, the waves travel back up the machine, superposing on the oncoming waves which they meet to produce patterns of built-up amplitude at some places and complete cancellation at others. The pattern that you see on this machine appears to be standing still, doesn't it? Various portions of the medium simply bob up and down in place without giving you the impression of motion in either direction along the machine. Observe that in this pattern there are places where the medium appears to be standing completely still all the time. These dead spots, or nodes, are exactly half a wavelength apart. Now let me show you something else. Under these conditions, the new waves which are continually being sent out by the generator superpose upon the previously emitted and multiply reflected waves in just the right phase to build up the amplitude to an abnormally large value, new crest on previous crest, and so on. The system thereupon becomes resonant, and the amplitude builds up to the noticeably larger value that you see here. Under these conditions, the new energy which is being fed into the system at each cycle is exactly equal to the energy which is being dissipated per cycle through friction at this new amplitude. Now, the initial adjustment which I made in the length of the machine to produce this resonant condition is called tuning. I could just as well have produced resonance by leaving the line at its original length and tuning the frequency of the generator instead. And I can destroy the resonant pattern that I have here by changing the value of either of these parameters a little bit in either direction. Another way of looking upon a resonant system is to regard it as a reservoir for energy. Thus, the escape wheel of a watch, a child's swing, a sounding organ pipe, the resonant circuit of an electrical radio transmitter are all examples of resonant systems. They exhibit abnormally large amplitudes of oscillation, and they possess relatively large contents of energy which have been built up by superposition over many previous cycles. Now, in this film, I hope I've been able to present you some different approaches and perhaps to lead you to a few new insights. One thing that has always profoundly impressed me is this: waves of all kinds behave alike. And if through any process you choose, you can learn the fundamentals of wave behavior, either through the study of some discipline in which waves play an important role, or even through the study of waves for themselves alone, then you will always feel at home in any branch of physics or engineering where the main show has to do with waves and how they behave.
This pile of dust, this heap of particles, is in a process of convection. The material travels inwards from the edge along the bottom of the pile, rises up in the middle, and is then carried back to the periphery. Even if the intensity of the vibration changes, there is still a whole system of radial circulation. At certain frequencies, or with certain tones, an extraordinarily interesting phenomenon is seen. Watch. We see two regularly and continuously rotating areas at either end of a diameter, going round and round like weathercocks. This is the expression of a rotating wave motion. We can see they are rotating in an anti-clockwise direction. In the vibrational fields of this lycopodium and of other materials, we saw time and again that in certain places the material is thrown up, then all is quiet, then it is thrown up once more, then all is quiet again. We saw that it kept to certain places, that it did not splash about just anyhow, but that everything took place in particular spots. And observation has shown that what we have here is an interference phenomenon. The action of the waves is cumulative. Their effects are summated at these spots, causing the mass to be ejected. Then quiet returns. Then there is another summation. Here we can see the currents running in contrary directions and creating a rotary effect or revolution. Here there is something very interesting to watch. Once again, we have interference. That is to say, there are two tones. One moment, the waves summate, then they cancel each other out. They summate again, and every time they summate, we have dynamics. And when they cancel each other out, we have rest and structural pattern. We see structure alternating continually with dynamics. Structure and dynamics. What we see then is not caused by switching the vibration on and off, but is itself a vibrational phenomenon. Structures appear, clouds are formed, there is movement and change, forms emerge, all as the result of interference.
This is a hologram. Holograms have little in common with traditional photographs, except that both use film. Holograms can create completely three-dimensional pictures, and every piece of the film can reconstruct the entire image. In order to understand holography, you have to understand something about waves. When waves meet, their effects are additive. When two crests meet, we get an increased effect. But when crest meets trough, their effects cancel out. This interference effect is important in holography. Here are two pure wave sources of equal amplitude and frequency. Notice the areas of motion and calm in the water. Within the film emulsion, areas are exposed as light waves move through. Where the wave fronts cross each other, the silver emulsion is exposed. The developed emulsion is essentially a thick diffraction grating. What would happen if the emulsion had been here, between the source and the object? In this case, the interference produces what is known as a standing wave pattern. These are standing waves. The lens in the holographic reconstruction actually works. This is the principle used in microscope holography. When a laser shines through a hologram and onto a screen, a two-dimensional image is projected. Even a small fragment can project the entire image. Holography is an efficient data storage medium, which may soon outdate traditional microfilm.
This is the Mandelbrot set, one of the most beautiful and remarkable discoveries in the entire history of mathematics. Yet it was discovered as recently as 1980.
The Mandelbrot set is real, an absolute thing, no question whatsoever. Any mathematician or any computer scientist or student in a school can study it and find the same, describe the same thing. It's a common experience. And so such things that can be magnified forever, that have infinite precision, do exist. But they're not touchable.
It's a geometrical shape, an icon, if you wish, which somehow embodies as an example a very important aspect of how the world works. Somebody recently actually called this set the thumbprint of God.
Infinitely complex. And when I say infinitely, I really mean that. Most people, when they say infinitely, they mean only rather big. But this is really infinity. What is so remarkable, in fact, astounding, about the Mandelbrot set is that although it's infinitely complex, it's based on incredibly simple principles, unlike almost everything in modern mathematics. In fact, anybody who can add and multiply can understand the principles on which it's based. You don't even have to subtract or divide, still less use logarithms or trigonometrical functions to comprehend how the Mandelbrot set is created. In fact, in principle, it could have been discovered any time in human history, and not merely in 1980. But the problem is this: although it's only based on adding and multiplying, you have to carry out those operations millions, billions of times to create a complete set. And that's why it was not discovered until the era of modern computers.
For me, the first step, or most difficult mathematical problem, was to program it and see how it looked like. We started programming these sets of all kinds. It was extraordinarily great fun.
The letters in the Mandelbrot equation stand for numbers, unlike those in Einstein's equation where they stand for physical quantities: mass, velocity, energy. The Mandelbrot numbers are coordinates, positions on the plane defining the location of a spot. Another difference from Einstein's equation, and a very important one, is this double arrow. It's a kind of two-way traffic sign. The numbers flow in both directions, constantly feeding back on themselves. This process of going round and round a loop is called iteration. It's rather like a dog chasing its own tail. The output of one operation becomes the input of the other, and so on and on and on. Now look what's happening. At the tip of each hair, it splits into two others, and so on. Each is splitting, going on indefinitely. This splitting up, this bifurcation, going off into apparently random directions quite abruptly, is typical of a class of mathematical entities called fractals. The Mandelbrot set is the most famous fractal.
The word fractal means any geometrical structure that has detail on all scales of magnification. No matter how big you make it, you still see extra new details you didn't see before. And the name was actually invented by Mandelbrot himself. He felt he had to have a name for this area he realised he was working in. And so he coined the term fractal because it conveys this feeling of fragmented, broken, fractional, irregular.
One of the revolutions in thought that's resulted from this discovery is the realization that nature deals not in smooth, continuous objects, as we always imagined, but more often in fractal. Much more elaborate structures can be created by very similar rules. I'd like to emphasize that all these shapes or objects, whatever you call them, although they look real, are generated entirely in the computer by following out a few simple instructions and repeating them over and over again. This is the way in which nature creates things.
It's exactly like the DNA in a butterfly's egg. Somehow that unravels and unrolls to form the extraordinary and beautiful pattern on a butterfly's wing with its myriads of colors and form. Somehow it's hidden in that seed in the DNA.
Let's go back to the Mandelbrot set and look at some more of the strange flora and fauna of the Mandelbrot Zoo. There's a certain similarity between these shapes. We recognize they're cousins of each other, and yet they're all different despite their similarity. There's an infinite variety here, just indeed as there is in the world of nature.
To me, just looking up at the Milky Way and staring at a fractal, it's got an extraordinary dotty character, and yet if you take a magnifying glass to it, that is a telescope, and you look at it ever closer, you find that there are hundreds and thousands more little dots where you thought there was almost none. So you get an immediate example of a structure that seems to go in and in and in with more and more detail.
I think there may be some connection between the Mandelbrot set and the wiring of the brain is because when I close my eyes and press things against my eyelids, I see these patterns. I'm sure you're all familiar with them. You also see them when anybody gives you a bang on the head. Well, sometimes these patterns echo some of the shapes of the Mandelbrot set. Also, I am told, I have never tried the experiment myself, that when certain illegal chemicals are ingested, you experience visual hallucinations strikingly similar to some of the patterns of the Mandelbrot set. Why do these strange patterns have such an appeal? Well, obviously they trigger some kind of resonance in the mind. And incidentally, there's an odd coincidence here. The name Mandelbrot and the word mandala, or a religious symbol. I'm sure it's a pure coincidence, but indeed the Mandelbrot set does seem to contain an enormous number of mandalas or symbols. The Paisley pattern is one, and I'm sure there are many others. And in ecclesiastical design, such as stained glass windows, particularly in Islamic art, you find many echoes of the Mandelbrot set centuries before it was discovered.
This is how God created a system which gave us free will. It's the most brilliant maneuver in the universe, to create something in which everything is free. How could you do that?
The Mandelbrot set is indeed one of the most astonishing discoveries in the entire history of mathematics. Who could have dreamed that such an incredibly simple equation could have generated images of literally infinite complexity? We've all read stories about maps that revealed the location of some hidden treasure. Well, in this case, the map is the treasure.